G'day, JSConf. So, what happened here? Yep. What's that thing at the top? We'll see if it disappears. Yeah. I think this is good to go now. Yeah, I did.
Does it say?
Oh, now it's back again. Okay. Yeah, okay, so we're good to go now. I'm here to talk about HyperJournal. HyperJournal is a tamper-proof publishing system. And what exactly that means, we're going to talk about now. So there's an issue here. HyperJournal doesn't actually exist yet. So this is going to be how to build HyperJournal, a tamper-proof publishing system. What we're going to talk about today is we're going to talk a lot about cryptography, and cryptography is very security sensitive. So if I say anything wrong, since we don't have Q&A here, you'll have to go and correct me on the JSConf AU repository I put up. And also, if you're going to apply any of the ideas in this this presentation, go and have a look there before you actually use any of the stuff I'm talking about. Yeah, next warning. Doctors have the Hippocratic oath, which is pretty much that you should always care for a person in need, regardless of whether they are able to compensate you. And pretty much every doctor in the whole world adheres to this oath. It goes all the way back to the ancient Greeks. In software development, we have a quite similar oath, and that's just don't roll your own cryptography. But yeah, we're going to do some dangerous stuff here today. So I'm actually not sure what people say when they say don't roll your own cryptography. I think they mean that you shouldn't go and invent your own like crypto algorithms, but it doesn't really make sense if you can't go and use cryptography. So today we're only going to use cryptography. We're not going to invent any cryptography. So start with the narcissistic part. My name is Emil Bay. Online, I'm known as Emil Bay because there's a famous mathematician called Thomas Bayes, and I want to associate with him. I used to study math at uni, but I was at the engineering school, but they didn't really teach it in an engineering way, so I didn't like it, and I ended up dropping out and just work on software. So I've worked at a high-performance computing lab with supercomputers, and I've worked at an advertisement agency, and most recently I've worked at a national newspaper in Copenhagen, Denmark. But now I'm working on a startup with a couple of other people called Commodity Trader, where we sell all kinds of agriculture products. So if you want to get hooked up with some Argentine high-protein soy, I'm totally your man, so just catch me in the break. Yeah, but really I'm just another hermite from the internet coming out of my shell today, here to talk about cryptography. Yeah, so what's up with HyperJournal? What's this all about? HyperJournal has a goal to provide a easy-to-use, cryptographically secure, integrated newsroom for distributed media organizations. So who are these distributed media organizations? And this is where all my motivation comes from. It comes from a project I've been working on with a couple of other people for the past maybe 9 months. We've been working with Syrian journalists in exile in Turkey. What we've been trying to do with them is, we have 7 newspapers. They are all against the Assad regime. They're all against ISIS taking over Syria. They just want a peaceful, united Syria again. And to try and help that come along, we have helped them develop a digital media called SNP. These are the 7 media organizations. So that's been extremely interesting. That's been working on a Arabic news site, and I'll just tell you, RTL support in all the browsers is like bomb, like shit. So these are the journalists, and you might not be able to tell, but this is life and death for them. Pretty much every single one of these people have gone through torture under the Assad regime, and now they're in Turkey. And the way they work is that they write their newspapers from Istanbul. They get their newspapers printed in Istanbul. they smuggle them across the border on big trucks, and they distribute free, so they don't earn any money at all. The way they survive is by doing a bit of freelancing work for Western media, and by the support they get from an organization called IMS, which is also the non-profit organization supporting all of this this work with S&P. Here's a couple of people I've been working with on it. So that's me over there, let's bearded. And then we have Anders, Emil, and Jacob. And these are the guys who are working with the people in Syria. Now, these guys not in Syria, in Istanbul, they have the problem that they can't go and report from inside Syria, both because they might face imprisonment and torture, but also because the whole war in Syria is about who tells the story that the rest of the world believes, and it's very hard to get your story outside of Syria. I don't know this firsthand, but this is what they tell me, is that since Russia got involved in the conflict, this whole landscape of what's truth and what's false has become even more complex. So Anders is, I met Anders at the newspaper I worked at. He was the technical director there, and he asked me to come and work on this project, and I immediately said yes, because I mean, in your life you need a profit project, something you can earn money from, but you also need a prosperity project, something that brings humanity forward. And this is, I think this is exactly one of those projects. But after we developed the website, he was asking me, like, is there no more, can we do something better? Because these websites that are against the Assad regime is extremely resourceful, also in technical regards. So anyone who goes against the regime, they'll get hacked, or attempted hacking. The Assad regime controls the whole telecommunications infrastructure inside Syria. So if they don't like your website, they might just use DNS poisoning to make people unable to access your website. And I mean, Syria is not that's one thing people get wrong all the time, is that it's not a developing nation. People actually have high-end smartphones there, and laptops and desktop computers that are pretty much up to standard with what we had here 3 or 4 years ago, before the war broke out. So we were like, what can we do to alleviate all these problems? It all coincided with also reading this book called The New Digital Age, written by Eric Schmidt, chairman of Google, and Jared Cohen, the director of Google Ideas. And in here, they talk about how can we make a media organization in the 21st century that how can we use technology to actually empower media organizations. And one of the things they talk about in there is that connectivity gives a new hope to freedom of speech, because you can report from an area and the reporting is done. You might send your reporting outside of the area that's under pressure, and there's no way for the local people in power to take down whatever you're saying. But it requires a couple of things. Imagine there's an international NGO whose mission is to facilitate confidential reporting. We need that because we need someone outside the country who are not answering to local legislation. Fortunately, IMS, who I've been working with, are exactly that kind of NGO. So yeah, that's that. Next thing they say is that in order to protect the identity of the journalists, you need to register them in the system under just a number, like a code. So you can't associate their identity with who they are in the real world. And this code they talk about, that's something we'll call a public key in this talk, which is a part of a cryptographic technique. And so the journalists and the editors, they communicate anonymously, and they only have to meet ever once when they do the employment, and that's to exchange this unique number, which we call the public key. So which problem do we want to solve again? We want to solve tamper-proof publishing, and especially over insecure channels. So what's an insecure channel? That's the internet is insecure. Carrier pigeons are insecure. Mail, telephone, everything is pretty much insecure until you establish a secure channel. So we'll use cryptography to do this. You can use cryptography to make secure channels, like we do it all the time with HTTPS. But since our problem here is that the internet might not be available in Syria, or like in this particular case, might not be available because it's controlled by one of the people we are fighting. We will have to go to other means. So the insecure channel might be carrier pigeons or USB sticks or Bluetooth networks or whatever. So to get started with cryptography, in cryptography we have something called ciphers, and ciphers is like the algorithms we use to do encryption and decryption, and it's defined like this. So we have a encryption function which takes a message, a plain text we call it, and it outputs a cipher text. You also have a decryption function which takes your ciphertext and makes it back into a plain text. And then you have some parameters, and some of them might be public, like which large prime number are we using, and some of them might be secret, like what's the key that we're using to encrypt with. So let's build our own first cipher. And so when you talk about ciphers, you talk about how much computational power do you need to crack the cipher, like who is your adversary. And this cipher we're going to build here has a threat model that says a determined fourth grader can break it. So you might be able to use it for sending notes in class, you might be able to use it to encrypt Christmas shopping list, or you might be able to use it to command legions across the Roman Empire. So, so this cipher was invented by Julius Caesar, and he used it 2,000 years ago to send military commands across the Roman Empire. And it's actually very simple. You might have invented this cipher yourself at some point. It's called a Caesar cipher. It's also called a shift cipher and a rotation cipher. What you do is that you take the alphabet, and then if you want to write A, you shift the alphabet over, and you might write C. So Caesar, he used the number 3. He shifted the whole alphabet by 3 letters. And this is actually the whole implementation for doing a Caesar cipher. You can see here that the encryption function takes in a plaintext. The plaintext in this case has to be a node buffer. I'll explain what a buffer is just in a minute. Then it takes every single byte in a buffer and it shifts it over. But the thing is with bytes is that they can only be values between 0 and 255. So what happens when we get to the last byte and we add 3 to it, then we get to like 258. And that's where we use modular arithmetic. I'll also explain what that is. Some people call it like clockwork arithmetic. So that'll just wrap the whole thing back around. So if you have 258, that'll wrap back around and become 2. Well, at least we can see it here. So quick intro to modular arithmetic. Clockwork arithmetic, because you can do it on a clock. A clock is like probably the most natural way where you learn modular arithmetic. Once the pointer arrow hand goes from 11 to 12, then from 12 to 1, there, you just rolled over from 12 to 1. It's all very natural. You also use it when you work with degrees or like time of course, and GPS coordinates. Like the way I finally grokked what modular arithmetic was about was when I was building this robot game, and once the robots got to the edge of the game, I wanted them to go back to the other side of the map, and that's just taking the modular of the width of the map, so it will automatically always wrap around. A good way to think about it is rotation. So up the top we have 0. And this arithmetic we're doing here has a period of 3, so there's 3 values you can have. If you take 3 minus 1 modulo 3, then you get from 0 minus 1, then you're down to 2. And every time you take minus 1, you rotate anti-clockwise. And every time you go up 1, you go clockwise around. In JavaScript, we have the percentage sign, and a lot of people call that the modulo operator, but that's wrong. It's called the remainder operator, so they're not exactly the same. Next thing, when you do cryptography, you're working with binary data all the time, so you use buffers. Who here knows what a buffer is? Okay, so good amount of people maybe. A buffer is just like it's just an array. It's just an array, but it's like the best thing we get to raw memory access in JavaScript. So you're actually going in and you're manipulating individual bytes in memory. In Node, it's backed by a typed array called uint8 array. It can take a byte in each cell, so a value from 0 to 255, and it's a default container. If you work with Node, you touch buffers at some point, because every time you get a HTTP request, all the data that comes in is wrapped in a buffer, so you have to do like toString, and then you get what's the actual contents in there. If you work with the FS module, you get buffers back all the time. So here's a couple of examples of how to do buffers. So the top one is just taking a string and converting it to a buffer. Next one, we say that we have an array of individual bytes, and we make that a buffer. And the last one is just allocating a fixed sized buffer that we want to use. So this is the Caesar cipher. Of course, it's a JS conference, so I like cats. So let's take and encrypt that. And once you encrypt it, this is the values you get down the bottom. And you can, of course, decrypt that as well. Now I'm going to show why the Caesar cipher is so weak. So we're going to go here and from the Gutenberg project, I've downloaded one of my favorite books, Robinson Crusoe. And you can see that it's just over 650,000 characters. What we're going to do is what's called a frequency analysis. And if you give this encrypted piece of text to a fourth grader, what they might notice immediately is there's a lot of characters that go again and again. That would be spaces. So that's really easy to see. And even though we shifted all the letters over, so the text is garbage, you can still see some letters are occurring more frequently than others. So if we formalize this and just count how many times do we have every single byte in the buffer, then we get a diagram like this. So here I've cheated a bit. The blue lines are the unencrypted text. The orange lines are the encrypted text. And you can see it's just all the bars have just been shifted over. If you count the shift, then you get the number 3. Another thing you could do if you didn't, of course you don't have the unencrypted text normally. One thing you can do is just take like a huge dictionary, take all the words in there, count the letters or the bytes, and then do the same kind of thing. And because of the law of large numbers, so if you have a lot of data, then this diagram should be pretty much the same. So okay, broken our first cipher. The whole science around cryptography and crypto analysis, so breaking ciphers, is what's called cryptology. So you can say that the Caesar cipher is essentially just security by obscurity, and we don't want that. So we can do better. We can actually do much better. We can do perfectly. So we're going to do the next cipher. And it's a perfect cipher. That means no matter how much computer power, even if you have a computer the size of the universe, even if you're God, you can't break this cipher. It's called the one-time pad. It's actually a really old cipher. It was invented in 1882, and it was rediscovered in 1917, and a guy took a patent out on it then. It has a couple of issues. The keys that you use to encrypt your stuff has to be just as long as what you're encrypting. So that's a bit of a bummer. If you have, you want to encrypt Robinson Crusoe, you have a 600 kilobyte file, you need a key that's 600 kilobytes. And how are you going to give 600 kilobyte keys to people? So it's not very usable. You do use it in very rare occasions, but it has a nice property that you can't break it whatsoever. And so here's an example of how to use the cipher. Up the top, we have one key. Then we, let's just skip ahead, and then we have the plain text. I actually like dogs instead, but that's not very popular here at a JS conference, so let's encrypt that. And the nice thing about the one-time pad is that you can make the text become whatever you want. So just below key B, that's someone who thinks they stole our key, but they actually got the wrong key. And if you take and decrypt with the key B, they won't know that they had the wrong key. It'll just decrypt, and also I like cats. So that way I have plausible deniability. Yeah. So keys are problematic because you have to share them. And how do you share keys? You need a secure channel. You need some way to tell someone securely without anybody else knowing what was the key for this ciphertext. And the only secure way I can think of that you can share these kind of keys is like a dark back alley. But you don't know if an adversary might show up and steal your keys, or I don't know, break your kneecaps or something like that. So this problem is called bootstrapping trust. How do you get to a point where you can actually start trusting other keys? Because once you have a secure channel, you can just start exchanging keys for other messages on that secure channel. But the whole issue is just how do we get started? So yeah, and you can't trust people on the internet because the internet is an insecure channel. But that's really not a problem because we're not too concerned about encrypting messages. We just want them signed, so they're tamper-proof. Like, could we just like put an enforceable signature on our message so nobody could change the message without us knowing about it? Turns out we can. So we can use hash functions. Who here has ever built a user system to take in passwords? Okay, I actually expected pretty much everyone to have worked with like passwords before. Because when you put passwords into a database, you usually take the password and you use something called a hash function on it. In this particular case, we are going to use something called cryptographic hash functions. And hash functions are magic. I mean, you need a PhD in mathematics to just understand how they work on a basic level, so I have no idea. But here's a way to think about it. And hash function is a function that takes like an arbitrary large file, so it could be like several petabytes of data, and it compresses it into like a tiny fingerprint. So it's pretty much like a fingerprinting function. You also call it a digest function. So yeah, very, very large binary things we call blobs. So you can take like a blob of whatever size, and you can hash it down, and it'll always be the same size. And the nice thing about hash functions is that it's deterministic. So every single time you hash something, you'll always get the same fingerprint. So this is how you do hashes in Node. You import the crypto module. Here we use a hash function called SHA-256. That's a secure hash function still. So you can go use that at home. You update the hash function with whatever data you get in, and in the end you call digest, and you get out your fingerprint. So yeah, what is this good for? First of all, hash functions have a couple of properties that make them usable to us. They are deterministic, so whatever data you give them is always going to be the same fingerprint. They take infinitely large, or like extremely large data, and they make like a tiny little fingerprint out of it. They are what's called one-way, so if you have a fingerprint, you can never figure out what data gave you that fingerprint without trying out all possible data in the universe kind of thing. And that's also what goes with collision resistant, like two pieces of data should never give the same fingerprint, because a fingerprint should be unique, right? So this is all like very theoretic and like hard to get a grasp on, but so what can we use it for in the real world? Well, on the internet, you can use it for e-tags. So e-tags are a way of identifying your data. It has to be unique, so a fingerprint is nice, right? Another thing you can use it for is what's called content addressable storage. I'm pretty sure all of you use content addressable storage on a daily basis. I don't know if you heard about Git, but Git is a content addressable storage mechanism. Every time you commit something to Git, you get out a little hash, and that's because whatever you put into Git will take that, hash it, and then fingerprint it. A hash is also a commitment. What that means is that you could take like a solution to some puzzle or something, hash it, and give the hash to everyone, and they'll know that you solved the puzzle, and then at a later time you could reveal your solution, and they could verify that you actually used the same solution previously. Password verification, you use it all the time there. In cryptocurrencies, you use it for proof of work, and you also use it for blockchains, but I hate the word blockchains because it's getting bloated, like big data got bloated. So the actual scientific word for a blockchain is a Merkle DAG. And you can also use it for file integrity. So file integrity means that you save the hash for a file, and then later when you go to read it again, you can just hash it and make sure that nobody has tampered with it. And that's exactly what we want to do. So there's a couple of hash functions out there. This was the first hash function I ever learned about. It's called MD5, but MD5 has been broken since I was like a toddler, so don't go use MD5. Okay, what's the next thing we have? There's a hash function called SHA-0, oddly broken as well. Stay away from that. Then we have SHA-1, and SHA-1 is actually the hash function that's used in Git. However, stay away from SHA-1 because there are theoretical attacks. It might be broken in the next 10, 20 years. So that's why it's okay for Git, because it's not really like 10, 20 years they have time to fix it, and it's not really that high value to break a hash in Git. But you might have seen all this trouble that's been going on recently with SSL certificates. getting out of hand, and like some of the certificate authorities have been getting threats from Mozilla and Google, and actually one of them, the Chinese one, is going to be banned next year. So don't go and use SHA-1. What you can use is the next family of SHA functions, SHA-2, where you have SHA-256 and SHA-512. Those are both the functions that are exposed in Node.js. And you can also use the one I use, which is called Blake2. And we'll see how to use Blake2 in just a minute. And I'll cue a joke. So some people might be superstitious and go out and get a number plate. So yeah, don't run into this guy. And I actually checked in Victoria, both MD5 and SHA-0 are available as number plates, while SHA-256 and 512 are not available. So some people out there are superstitious. Just a little side note, once we're talking about hash function, is that if you go and encrypt passwords, don't use any of the hash functions I just talked about, because they're very easy to parallelize and not very good for passwords. There are specific functions out there designed just for doing password hashing. The most recent winner of the password hashing function was the argon2 function. scrypt has bindings in JavaScript as well. PBKDF2 is built into no crypto module. Okay. I was going to talk about how to do blockchains. I think it might take a bit too much time, so I'll just skip over that. So the problem with hashes is that anyone can compute the hash. You don't know where the hash came from. So if you have a source inside of Syria and you want to make sure that whatever they're saying is actually from the same person that you thought it was, it's reliable, it doesn't really work to just take the continent hash, because if someone shoots down his carrier pigeon and reads what's on the SD card and he doesn't like what's on there, he just changes it, hashes it again, and you have the integrity is still preserved of the file, but now it was someone else who modified whatever you're trying to get out of the zone. So we have to do real-world cryptography. And you have a choice here. The crypto bindings in Node bind to something called OpenSSL. You might have heard that OpenSSL has had a couple of issues in the past years because the code quality, there's been a lot of bit rot, and the C code that's in there is pretty hard to follow, so that's why a lot of bugs can sneak in. But we have an alternative. You can use something called NAGL, which stands for Networking and Cryptography Library, which is all very clean implementations of very modern crypto functions, like the Blake2 function I was talking about before. And you can use libsodium, which is my favorite, which is a derivative of NAGL. This is how you would go. This is the module you would go and install if you wanted to use sodium. It was written by one of my friends, Matthias, and it was released just 2 days ago, so it's very new. So, how am I going for time here? If we want to make sure that the content that was sent out of wherever was actually from the person that we thought it was from, we can use something called asymmetric cryptography. Asymmetric cryptography is where you have a public key and a private key. So you're using asymmetric cryptography all the time. SSL is based on it. When you do Git, you also give your public key to GitHub so they can know that you are actually the one sending all the file content to GitHub once you do a Git push. Sometimes you also call the public key the identity, because now your name is your public key, and you call the private key the secret key too, because you're never going to reveal that. So if you have someone's public key, then you can send them messages. You can just take the message, encrypt it with the public key, and you need to have the private key to decrypt it. So that's really nice in the way that you know that you can just get public keys. That should be public anyway. So you can just get public keys from all your friends and use that to send them secret messages. You can also do another thing which is very counterintuitive. You can take your own private key, encrypt the message, and send it out to the world, and then everyone who has your public key can decrypt it. But that doesn't really make a lot of sense, because then, what's the point of encrypting something if everyone can decrypt it? Well, yeah, exactly. What you can use it for is signatures, and these signatures work just like in the real world. You take your file, you hash it down, you encrypt it with your private key, and then everyone who has your public key, they know that you own that public key, and they can decrypt it and see that this was actually a hash that you encrypted, because only you has the private key. This is in cryptography lingo called non-repudiation, because there's no way to dispute that you were the one actually encrypting that file. So how does the signature work? Well, first you need a key pair, like a public and private key. So you do that like this. Then you have your data, and you hash the data, and then you encrypt it with your private key. Yeah, I'll just skip over this. This is a quick introduction to how to do it with emoji. So I'll just skip over this. Okay, yeah, now we have tamper-proof publishing. This is all it took. It's all about cryptographic signatures. There's still quite a number of issues with HyperJournal, and that's why I didn't want to publish or release it today, because this is very sensitive software, so I want to be very sure that what I'm doing is right, and that the algorithms I'm actually using them in the right way. But I have a number of open problems, like delivering content to readers. So today I've only talked about how to take content out of a war zone maybe, and making sure that the person who wrote it is actually who you thought wrote it. But what if you're a reader inside an area where you can't just access the public internet? Then you might want to have an app or a website that can verify the content. Because if anyone is in the middle swapping out all the content for content they like propaganda, then you want to make sure, or you want to be able to tell that it was actually swapped out in the middle. Secure communication, so like one thing is to just sign your data, but it's not encrypted. So, I mean, anyone could read it, and in the actual real world, whatever you're saying might be sensitive. So actual encryption is something I want to build in there too. Another problem, a couple of problems that you have if you're saying something that other people don't like is that they might try to send you a denial of service attack, and that's becoming a very real threat now. Google has a project called Project Shield, which is actually aimed at helping journalists who are affected by DDoS attacks. There might be fake SSL certificates, so that means that we can't really rely on HTTPS, or well, we can, but if you are up against a government adversary, then they might just go to the certificate authority, the guy who makes all this SSL certificates, and say, hey, give us the keys. Another thing is DNS poisoning, which is something they've experienced in Syria, because it is the guy you're fighting who's controlling the communication medium you're using. And then we have the really, really bad guys. And the really, really bad guys, it doesn't matter how good your crypto is, because they might still be able to break your kneecaps, kind of thing. And that's also illustrated in this XKCD comic. So yeah, it doesn't matter if they're not just going to go and say, well, we can't break the crypto, so we're just not going to bother. They'll just go and get you and do bad things to you. So I'm not the only one working in this space. There's a lot of projects out there working on exactly this stuff. The blockchain stuff, if you want to look at that, it's called the Merkle DEX. There's a couple of projects that do that. Secure Scuttlebutt is something that's extremely interesting. It's a federated, totally distributed peer-to-peer social network that uses all these cryptographic primitives to make sure that only you can write to your friends and all that. Then you have, of course, the BitTorrent stuff. You have WebTorrent, and you have Matt McKeck, who's going to play tonight. He's made Ferment, which is an excellent tool. It's like a SoundCloud clone, but without anyone owning it. There's also the excellent DAT project, which my friend Matthias is working on, and a couple of other friends, which is for sharing scientific data using all this cryptography and peer-to-peer technology. So that's what I had to say. Thank you.